Hello everyone, my name is Runyu and my teammate is Haoyu Zhang. So the topic of our mini project is TCP and explicit congestion notification. Okay, so the presentation will include the six-part background, ECN experiments done by the researchers, implementation issues with ECN, the conclusion and the reference. Okay, let's go to the background. So we will talk about the congestion control in TCP, in this course. There are many three parts, three states here. The slow start, which will happen at the start of the transmission or after the timeout of a packet. The congestion avoidance, it will happen after the size of the congestion window arrive at the threshold here or after the fast recovery. And the fast recovery happens after the sender receives 3 duplicate X. In this case, the sender will retransmit the packet, set the threshold and the window size here. Okay, so although the routers have the congestion control mechanism, there are still several problems here. The current routers cannot detect the incipient congestion. Instead, they can only know the congestion after the packet drops caused by the queue overflow. So in this case, they need to retransmit the packets, which will increase the delay and reduce the throughput. To solve these problems, there are several ways. The first one is the random early detection, which is also included in the course. If the average queue size arrived at the threshold, the router will randomly drop the packets to inform the sender that the congestion happened. Yeah, and for the ECN, which we'll discuss more in this presentation, the routers can compute the average queue size as well. Instead, they can set the BCN bit to send the information of the congestion to the sender. And there are several advantages of those solutions here. They can reduce the delay and increase the link utilization. For the ECN, it can also make it possible for the TCP/IP traffic to traverse the networks that have their own congestion control mechanisms, such as the ATM. So apart from the drop detect method, the ATM can also use the ECN bits to detect the incipient congestion. Okay, let's go to the ECN itself. So there are some current ECN mechanism. The first one is the source quench messages. The mechanism tells that a router or a host will send ICMP source quench messages when it receives datagrams at a rate that is too fast to be processed. That is, the congestion happen. Although it can detect the incipient congestion here, but it is clear that it will bring about extra traffic to the link, which will consume the bandwidth of the link. So in this way, it is not effective. For the decibit congestion avoidance, the mechanism is that the gateway will set the ECN bits in the packet header according to the average queue size. If the half of the packets in the last window have the ECN set, the window size of the sender will decrease in this way. However, it also have a disadvantage. This technique does not allow for the effective use of the lines because it fails to take advantages of the available bandwidth. So based on those former mechanism, Sally Floyd proposed another ECN. Here is the 6 guidelines of the new the proposed ECN. The first one is that over the long time scales, TCP response to ECN should be similar to this response to a dropped packet as an notification of the congestion. These tips make sure that the ECN can work. And the second one, over the smaller timescales, TCP's response to ECN can be less conservative. This is because it is just incipient congestion detection, so the sender does not need to respond it very intensively, which can make sure a higher throughput. And the third one, a single ECN should trigger the response to the congestion, which is different from the decibit we talked before. And for the first one, the TCP should react to an ECN at most once per RTT. The purpose of these tips are same as the second one. It makes sure that the TCP does not respond to the ECN too often, which may reduce the throughput. And for the fifth one and the sixth one, they make sure that the TCP will work correctly based on its basic rules.
Show you the ECN experience, the results, and the conclusions. Let's start with the simulation of ECN. For the version of TCP, this paper used fast recovery congestion control algorithms in random TCP as well as the slow start, congestion avoidance, and fast retransmit algorithm in the early TCP. For the simulations in this paper, the RED gateway was given an option to set the ECN bit in the packet header rather than dropping the packet, as an indication of congestion when the buffer had not yet overflowed. When the TCP receiver receives a data packet with the ECN bit set in the packet header, the receiver sets the ECN bits in the next outgoing ACK packet. The simulation scenario in this figure consists of 5 bulk data TCP connections and 10 telnet connections from 5 sources feeding into a single congested link. The simulations shows that for the networks with ECN, the throughput of the bulk data connections is high, and the telnet packet delay is low, regardless of the buffer size, the TCP clock granularity, the TCP window size, or the RED gateway variation. Thus, the simulations with ECN are robust, delivering essentially optimal performance over a wide range of conditions. In general, the simulations show that the ECN performance is less sensitive to the network parameters, and that the use of ECN can improve both delay and throughput. However, while the simulations show the benefits of using ECN, the simulations show that under proper conditions, it is possible to get reasonable performance without ECN. In this slide, we can see the results. Bulk data is not sensitive to delay, so evaluation criteria is throughput. However, telnet is sensitive, so researchers use delay to evaluate. In this experience, they ran 5 simulations for each set of parameters. The result of each simulation is marked on the graph, and the lines show the average of the 5 simulations. As these results shown, for the simulations of RED with ECN, the effective throughput is high and the telnet packet delay is low. Without ECN, the network performance can be significantly affected by the TCP clock granularity, by the level of congestion, and by whether the RED gateway is using a drop-in policy that is sensitive to packet size. And in this part, I will discuss the advantages and disadvantages of ECN based on the above experiments. The first problem is that a non-compliant TCP connection could set the ECN field to indicate that it was ECN compatible and then ignore ECN notifications. Another problem with ECN messages that has no counterpart with packet drops is that an ECN message could be dropped by the network and the congestion notification could fail to reach the end node. Thus, neither source quench messages nor the use of ECN fields in packet header can guarantee that TCP source will receive each notification of congestion. The gateway will continue to set the ECN field in randomly chosen packets as long as congestion persists at the gateway. In addition, a gateway implementing RED algorithms is particularly unlikely to drop a high fraction of packets. The occasional loss of an ECN message should not be a serious problem. The last one is for a wide area network. The overhead of source quench messages makes their use problematic. However, the logistical difficulties of adding ECN fields to IP packet headers makes the use of ECN field problematic as well. The proposed IP packet header has no space allocated for an ECN field. For the advantage of ECN, a main advantage of ECN mechanisms is in avoiding unnecessary packet drops, and therefore avoiding unnecessary delay for packets from low bandwidth, delay-sensitive TCP connections. A second advantage of ECN mechanisms is in networks, where the effectiveness of TCP retransmit timers is limited by the coarse granularity of the TCP clock. Here is the last slide. We will discuss the difference between these two methods. One of the advantages of using ECN fields is in packet headers is that the ECN field places no additional load on the network in times of congestion. If a drop tile router were to send a source quench message for every packet dropped at the router, the overhead of this source quench traffic in times of congestion could be a significant problem. In addition, in particular environments such as LANs, where the overhead of source quench messages would be limited by the small number of hoops on the return path, the use of source quench messages could be quite justifiable. For advantage of source quench message, the notification of congestion arrives at the source as quickly as possible. Also, source quench messages could be used immediately in appropriate networks. Given modified TCP implementations with the response to source quench messages proposed in this paper, the use of an ECN field in TCP/IP networks would depend on the presence of the ECN field in IP headers. Finally, these are references in these slides. Thank you for watching this video. Wish you have a nice holiday. Thank you.